Proteins are essential components of all living organisms. They play a crucial role in many biological processes, including cell structure, metabolism, and immunity. Studying the three-dimensional structure of proteins is fundamental to understanding their function. One of the most powerful tools for determining protein structures is X-ray crystallography. In this video, we will explore the process of protein crystallization and X-ray crystallography. Before we can determine the structure of a protein, we need to obtain high-quality crystals. Protein crystallization is a process of growing crystals of a protein in a solution. But why do we need the protein to be in a crystalline state? Well, the crystalline state corresponds to the state of atoms, ions, or molecules that are distributed in a regular and repetitive way. Amorphous solids are shapeless and have an irregular arrangement, with no defined geometric shape. Now, unlike amorphous solids, crystalline solids have equal intermolecular forces between them and distinctive flat surfaces or faces. Thus, when crystalline solids are exposed to X-rays, they diffract a pattern that is dependent on the internal structure of the crystal. Growing protein crystals usually involves a purified protein being dissolved in an aqueous buffer with a precipitant like ammonium sulfate or polyethylene glycol, where the concentration of the precipitant is just below the precipitation point of the protein. While water is removed by evaporation, both the concentration of the protein and the precipitant will increase to produce a crystal. A common method used to allow for the protein and precipitant solution to equilibrate is Weber diffusion. In this lesson, I'll talk about Weber diffusion using the sitting drop method. A reservoir of the precipitant solution is added in the large well, and equal amounts of the purified protein and the precipitant solution are added in the small well as a drop. The small well is where the crystal will form. A cover slip is added to create a tight seal. Since the precipitant solution that is appropriate for the crystal formation for any particular protein is usually not known, commercially available crystal screen packages are often used at this stage. That is, cocktail solutions of different salts, pH, and precipitant combinations can be screened on 96 well plates. If you get a hit crystal, then you may tweak the concentrations of the particular cocktail solution in another screen to get a better crystal. At this stage, we may also add a cryoprotectant like glycerol. This will be helpful later on preventing ice crystal formation when flash freezing. A good crystal has optical clarity, smooth faces, and sharp edges. Be wary of broken or twinned crystals. Now, once you have crystal of the desired quality, it's time to mount our protein crystal to a loop to be transferred to the X-ray diffractometer. We need our loop fitting the crystal size, a plate with the cryoprotectant solution, and a flash filled with liquid nitrogen. You can determine the size of the loop required by looking under the microscope and comparing it with the crystal before removing the cover slip. The chosen loop size should only be slightly larger than the crystal. Now we need to work quickly to prevent the evaporation of the protein drop and gently to avoid damaging the crystal. Place the crystal into the cryoprotectant solution by touching the loop to the drop and plunge it to the liquid nitrogen. The cryoprotectant is vital in preventing the formation of ice crystals and damaging the protein crystal. Now the crystals can be packed in a cryovial stored in liquid nitrogen and sent to the synchrotron. A synchrotron works by accelerating electrons to almost the speed of light. These electrons produce what we call a synchrotron light that predominantly lies in the X-ray region. An X-ray is a form of light that has a wavelength about the size of an atom, thus allowing us to visualize our macromolecule at the atomic scale. These high-energy electron beams are directed in magnets in storage rings. The loop holding the crystallized sample is now positioned at the head of the goniometer. The goniometer holds the crystal in the beam of X-rays and rotates it to precise degrees, This allows the crystal to be struck by X-rays in all its different orientations, as to collect enough data for diffraction. A liquid nitrogen stream is used as a cryostat. As said at the start of the video, when we fire X-rays onto the crystal, it diffracts or scatters the beam into hundreds of intense rays. The diffraction pattern is dependent on the internal structure of the crystal. By measuring the intensities and positions of the spots, we can work out the structure of the macromolecule we are interested in. The diffraction image on the left shows one plane of the three-dimensional diffraction pattern of a crystal. The characteristic array of spots is referred to as reflections. The image on the right shows the electron density derived from the diffraction pattern. The resolution of the map is dependent on the quality of the crystal. The better the crystal, the higher the resolution, and the better interpreted the model of the molecular structure of our protein. To get from the right image to the left, we use mathematics to work out what each reflection means. We always need two pieces of information to create an electron density map: the amplitude of X-rays in each reflection and the phase of the X-rays in each reflection. The amplitude is calculated from the intensity of the spots we call reflections. The phases, however, are more complicated to measure. One of the methods used to overcome the phase problem is molecular replacement. This involves the use of previously solved protein structures as starting model, and phases are calculated based on them. Since the protein data bank now has more than 200,000 structural models, there is often a possible starting model available for molecular replacement. A very recent development in structural biology is the use of AlphaFold. This artificial intelligence program is able to make predictions of protein structure based on the amino acid sequence of a protein with high accuracy. Although this still has its limitations, atomic models developed in AlphaFold may be also used in molecular replacement as a starting model. Now that you solved your protein structure, you're on for a long journey to understand how your protein works through the study of interactions, the designing of drugs, and much more. Ευχαριστώ για την προσοχή σου.